this video we're going to go over how to calculate the equilibrium constant. So it can be calculated from this equation, which involves Gibbs energy, gas constant and temperature. exp is e to the power. So we have an example here with a reversible reaction. We're given some data at 298 Kelvin or 25 degrees Celsius. We're going to assume that the specific heat capacity is temperature independent, so it doesn't change as temperature changes. In real life it does change, but for the simplicity of our calculations we're just going to assume this. So calculate the equilibrium constant for this reaction at 1 bar 298 Kelvin. So to calculate Gibbs we use this equation, minus T. So this is enthalpy and entropy, and that little circle means it's standard temperature, which is 298 Kelvin. So we're going to calculate the standard enthalpy of reaction. Now we're going to use we're given the standard formations, enthalpy of formations for these substances. So because we have on the left hand side, so it'd be 126.9 and then minus 35.1 minus 393.5. And then if we do that sum, that leaves us with 178.3, and the units are in kilojoules per mole. So that's for enthalpy. For entropy, we do the exact same thing. We minus the reactants and plus the products. If we assume reactants, products. So we have minus 92.9 plus 39.8 plus 213.7. We add that all up. We get 160.6, and units are in joules per Kelvin per mole. So now we can calculate delta G. So we have, if we have it in the same unit, so we get the right answer. We have 178 multiplied by 1000 minus 298 is 298 Kelvin, and that's multiplied by, we have the entropy, so 160 plus 6, and that equals so that gives us 13441.2. And we have units joules per mole because we converted from kilojoules to joules. So now that we've got the delta G, the equation we were given, we can now find out the equilibrium constant. So K equals exp, so we have minus 441.2, and that's all over 8.314 multiplied by 298. So we have e to the power of minus 13441.2.314 multiplied by 298. And that gets us to 1.36 times 10 to the minus 23. So if we do another example, it says here, calculate the equilibrium constant for the reaction at 1 bar and 1000 K, so 1000 Kelvin. So with the temperature change, because we no longer have that little circle, which means standard temperature, because it's no longer at standard temperature, we have to use a slightly different equation to get the equilibrium constant, but it still uses the values on the table on the other side. So for this one, we need to use different equations to calculate Cp, delta entropy, and delta enthalpy. So using the values on this table, I've them written down on the side just because I'm going to flip the page. We're going to do the exact same thing, but find out the values at 1000 Kelvin. So to work out the delta specific heat capacity, that is minus plus 42.8 plus 37.1, because we minused the reactants and added the products, just like we did here. So we've got those numbers, and it comes out to minus 32, and that'll be joules per, what is it? Joules per Kelvin, yep. I forgot which one it was in. Moles per mole. That's a bit ambiguous. I'll just write joules per Kelvin per mole. So now we do the same for enthalpy, because it's no longer at standard temperature. We don't use that little circle. Just use a small notation of 1000 to show that it's at 1000 Kelvin. So we would need the original enthalpy plus the specific heat capacity, the final temperature minus the initial temperature. So if we do that, we calculated this enthalpy on the previous question, which was 178,300 joules, in joules, minus 32, because we've just worked out delta Cp, so that should be delta, minus 32. Our final temperature was 1000 Kelvin, and the initial, or the standard temperature, is 298 Kelvin. So if we plug that into calculator, we get 155,836 joules per mole. Now we need to work out the entropy. Entropy is similar, but the equation is a little bit different. So we need the standard entropy, like before. This time we're going to use delta Cp times the natural logarithm of the final temperature divided by the initial temperature. So if we add those numbers in, we have 160.6 from the previous example, minus 32, which we calculated here, times the logarithm of 1000 divided by 298. So if we put that into the calculator, we have 121.86, and that will be in joules per mole, and Kelvin as well, because it's entropy. And then we can use the equation to work out delta G. So delta G is 155,836 minus 1000, because we're at 1000 Kelvin, and that's multiplied by 121.86. It's the equation, this one, which is the equation to work out delta G. And then we put that into the calculator. Minus 1000 times 121.86, and that gives us 33976, and that'll be joules per mole. for delta G. Now that we've got delta G, we can plug that back into the equation we were given at the beginning to find out the equilibrium constant. So just a reminder, that's K equals E minus delta G over RT. So K equals E to the minus 33976 over RT. That gives us 0.0168, and that's it.